Hey folks, welcome back. Here's another hopefully helpful video about factoring. This one is about what we call quasi quadratics, and I call them that because they work like quadratics, but you wouldn't know it at first, okay? So quasi quadratics are basically gonna be expressions or polynomials that when we factor them work very similar to quadratics in the sense of how we factor them in the past, but when we look at them, we're not going to be able to notice that at first. Okay, but what I'm going to show you is some very similar patterns, just like we've seen before, and what I'm going to do is I'm going to show it to you side by side, one of which we've worked with, familiar, one of which is newer, but it's going to work the same way. It's just going to be the power of the variable will be different. All right, so without further ado, I'm going to slide on down, and let's take a look at our first example here. So observe we have x squared plus 3x plus 2, and we have x to the fourth plus 3x squared plus 2. Okay, very similar. This one is an x to the fourth and an x squared, and this one is an x squared and an x. But notice it's very similar, okay? So remember, when we factor, all I'm looking to do is to break it down so that when I multiply these things or FOIL them out or box them out or whatever method you use, when I multiply them, I get back this original thing. So here, what I would do is I know that if I have x times x, that's going to give me my x squared. And then kind of by trial and error, I might play around with different ways to multiply to 2, such that when I do all the foiling out, the x's add up to 3. And in this case, what we would get is we would get 2 and 1. And if we do it out real quick, we have x squared plus x plus 2x, so it's a total of 3x plus 2. Now this one over here is very similar, okay? Here it's a little bit different though, but notice one quick thing when I do this. So the first thing I'm going to notice is, well, how could I make x to the fourth? And remember from our exponent laws, if I have x to the m times x to the n, remember what happens? The exponents add, okay? So now let's take a look. If I have x, and this, by the way, is true no matter what variable you use. The letters, in terms of the x, those don't matter. They're just different ways of expressing the same idea. And right, sometimes we might have letters mean different things, right? If we're talking about time, we would use t. If we were talking about, I don't know, flowers, we'd use f, though that's kind of difficult because we wouldn't want to get that confused with the function. If we were talking about ice cubes, maybe we'd use c for cubes. All right, so the letter doesn't matter in terms of the overall math, right? So that's just something to think about. So now, how do I get x to the fourth? So I do my x, instead of x, I'm going to do x squared. Because notice, x squared times x squared, that gives me the x to the fourth. Now observe here how I also have an x squared. So now, unlike here, notice how when I multiply my number here, I get something x. When I multiply my number here, I'm going to get something x squared. But the idea is still the same, right? So if I want to multiply by 2, if I use 2 and 1, observe how I'll get x to the fourth plus 2x squared plus x squared. So let's show it out. X to the fourth plus 2x squared plus 1x squared plus 2. And again, these combine for 3x squared. So notice how we're going to get the exact same answer. It's just that now we have a quasi-quadratic. It's not a quadratic in reality. We would call this a quartic. But when I factor this, because of how these terms are lined up, what I end up getting is a solution that can be reached in much the similar way as with this. All right, so what I'm doing is I'm using what I know about quadratics to factor things that are not quite quadratics. Okay, so I recommend if you need a second to kind of think that through and digest that you take a second and do that, or otherwise I'm going to go ahead and I will move on to the next problem. All right, so I'm going to go ahead and I'm going to move down to the next set of problems here, okay? So here I've got another type of situation. Here what I have is a perfect square. I know that because something times itself is 4, and that same number plus itself is 4. In other words, the number times itself is C, and the number plus itself is B. And if I didn't know that, I would try to factor this out. Okay, so I'm thinking, all right, multiply to 4, add to 4. Well, that, my friends, is 2 and 2. Okay, so in other words, it's v plus 2 squared. See if this works over here. Now notice, similar thing. And sorry if you can't see, this is actually a 4 next to the v cubed. So let's see if I do the same thing here. And I'm just setting up my parentheses and working it out. So here, I set up my v cubed and v cubed because remember, due to the laws of exponents, okay, when I multiply these, the 3's are going to add to give me the 6. And again, notice how, again, that power of v is exactly the power that comes up in this thingy here. So now what I'm going to do is, similarly, if I write a 2 and a 2, I'm going to get v to the 6th. All right, so that's my v to the 6th, giving me what I need there. Then I've got my 2v cubed plus another 2v cubed. That's a total of 4v cubed times 4. Okay, so I get exactly the same thing. And notice how this is a perfect square. It just doesn't seem like it at first. So again, the idea of really using the structure, really using the concepts that we use with quadratics with things that are quasi-quadratics, right? They work like quadratics, but we know that they're not. Now, in this case, we're tempted to say, uh-oh, is this a difference of cubes or a sum of cubes? Not really, okay? Because if we assume we're going to use the integers, this is a cubed, but this is not a cubed. Okay, so we would have to think about that. All right, so I'm going to go to my last example. Oh, my favorite, a difference of squares. Okay, so a difference of squares. Now, actually, I technically, and people are might get picky with me, this is technically a difference of cubes, and that's okay. I'm going to show this to you as a difference of squares. But yes, this is a difference of cubes, and there may be a future video on that, but bear with me on this one. So with the difference of squares, we know the rule here. We have a p minus 1 and a p plus 1, because when you do this out, right, this p and this negative p cancel, and you just get the p squared and the negative 1, okay? Now, similarly, notice how this is a square too, because p cubed squared, well, remember, when you do a power to a power, these multiply, okay? And they get you p to the 6th, because that's 3 times 2. And now negative 1 times 1, negative 1 is 1 times 1. So we've got p cubed minus 1, p cubed plus 1. And again, you're going to see, right, difference of cubes, sum of cubes, and that's all right. But notice how the exact same idea here, okay? The only difference is we have a quasi-quadratic because it doesn't look like a quadratic, but it is, in fact, a quadratic, okay? It just doesn't look like that at first. Okay, I'm going to give you one more example down here of a quasi-quadratic that's similar to that. And what I've got for you is a 3n to the 6th minus 12, okay? Now, first thing we're looking for is what's going on here. This is a greatest common factor. Okay, so first thing we're going to do, take out that GCF. Oh, nice. Okay, so notice that comes out, and it's not a quadratic, but it is a quasi-quadratic because n cubed squared is equal to n to the sixth, and 2 squared is equal to 4. So this is a difference of squares. So I factor this, and remember, this is the one thing we got to make sure we work on. Bring down that GCF. That's part of everything, all right? And remember, I make that mistake too all the time. It's a totally understandable mistake, all right? But we got to be able to catch ourselves there and fix that up, okay? So what I'm doing here is difference of squares, right? N cubed times n cubed, n cubed times 2, n cubed times -2, so those cancel, and -2 times 2. So again, even though this was not a quadratic, we were able to use the ideas of quadratics in order to solve them, and that's why we call these quasi-quadratics, because when we factor them out, they work like quadratics, but you wouldn't know it just by looking at them at first, okay? So with these ones, it's going to look intimidating. You're going to see big powers of x. You're going to say, wait a minute, what am I going to do here? But you have to be a pattern hunter. You have to be able to look at those, and you have to be able to remember looking for those patterns. So I'm going to do one more, right? So let's say I was given 50 v to the sixth plus 60 v cubed plus 18. Okay, you guys try this. Take a second, try it. Pause your video, and then I'm going to show you the answer in just a moment. All right, this is a quasi-quadratic. Again, now it's not easy. We got to think this through. First thing is, let's look. GCF. So we got to take that out. This has a 2, a 2, a 2. Now those of you who might be saying 3, good. You saw the 3's, but this doesn't have a 3. Those who are saying 10's, good. But this does not have a 10. Okay? So I'm going to take out the biggest power I can, or the biggest number I can. In this case, no v's in common with all 3 of them. So I take out a 25v6. Okay, hopefully you got that. Lovely if you did. Okay, and now I'm going to take out a 30v cubed. Okay, and now I'm going to take out a 9. Okay, and now it's a quasi-quadratic because it doesn't look like a quadratic, but notice the v to the 6 and the v to the 3. That is a good sign of a quasi-quadratic. So let's take a second and think about this. Okay. All right. So I need 25v to the 6. So a good guess here would be 5v cubed and 5v cubed. Okay? And the reason I say that is because 5 times 5 giving me 25. V cubed times v cubed give me v to the 6. Now, if you went 25 and 1, okay. Only thing is, remember, when you add the v cubes, you're going to shoot way over 30. That's the problem you're going to run into. Okay? Now, how could I get 9? Well, again, this would be a place where you play around with it. Maybe you do 9 and 1. If I did 9 and 1, it would be 9 times 5, which is 45. Plus 5 times 1, which is 5, so I'd be at 50, way more than 30, okay? Notice how switching the 1 and the 9 doesn't matter. So what if we did 3 and 3? Well, notice 25v6, because remember, these add, plus 15v cubed, plus 15v cubed, plus 9. All right, so here we go. That's what we're looking for. And it's 2, I'm getting ahead of myself, right? I love that greatest common factor. 2, and then remember, something times itself, 5v cubed plus 3, And what power do I put on here? If there's two things, I put the squared, okay? So a lot going on here. Now, for full credit, if you want that big full credit answer, it really is important now. You got to be able to really break it down. If you get it down to this part, I really got to think about it. I mean, mathematically, they're the same thing. So I would be in a place where I'd have to really think personally about how I want to assess the full credit there. But again, here's the idea. Just like with quadratics, we're hunting for patterns, okay? We're using those patterns to our advantage, okay? And then we're trying to do our best to use these things that we learned with quadratics to help us when we have things that are not quadratics, okay? Because once we can break it down to this, then we got some rules. We got our sum of cubes. We got our difference of cubes, okay? Stuff like that. Because eventually we might want to graph these things, and we're going to need some of these analytical tools and patterns in order to be able to make that happen. Okay, so I hope you found this video informative. I really appreciate you taking the time to kind of see this through. I really encourage you to watch through it again, work through it again, and really do your best to try to understand these ideas, because as they start to build on each other, it's really important that you don't get lost in these ideas. And remember, all right, don't ever forget, you can do it. All right, I believe in you. I know you can do it. Keep up the good work, and you have a wonderful night. And remember, don't forget to love math.